Okay, so this is Year 13's SHM, Simple Harmonic Motion or Oscillations. So this is an experiment we're going to do in class. Essentially you're going to cut up a circle into equal sort of areas. Find that if you do that and graph the angles to a certain height, you're going to get a sine curve. So essentially saying that if you had something rotating around in a circle, it can be shown by a sine curve, like this sort of thing here. And another way of doing it, if this little object here was going around in the circle and you had the light shining, then it would show a shadow going up and down the screen here, and as the paper rolled over, then it would draw that path as it went through. And so this is what happens when, let's say, looking at a spring going up and down. Okay, as it goes up and down over time, so just up and down in one spot, if you sort of dragged a piece of paper past that spring, it would follow a SHM curve, a sine. So what we're going to do is we're going to consider a mass on a spring. Now this mass is going to be flicked upwards away from the equilibrium point, and it's undergo SHM. In other words, we've got a mass on a spring and we're going to flick it upwards. Okay. Motion of this mass can be represented by a rotating vector. In other words, a vector going around a circle. So for example, here's the mass on the side. Okay, it's going to have amplitude A. Okay. This is the equilibrium point. The equilibrium point. This thing is a spring. Okay, going up there. I could keep going. And so the mass is going up and down. Okay, so up and down. Now, at any one time we have this vector A. Okay, which is length amplitude. Okay, this will be an angle theta. The height will be x. Okay, and this is going to be at any time you're going to have this height x. Okay, so some certain time you get that height x. We're going to start off at 0. Okay, so at the point there, time equals 0, and as we go around, we're going to be going around at a certain angular velocity. Okay, so certain radians per second. Now, as the vector rotated at the angular velocity omega, the vertical component of the vector represents the displacement. Okay, so looking at the triangle, A is the size of that vector we had in the triangle. This side would also be A, but that doesn't matter. Going up here, we've got a vertical component change in x, okay, and it's going to be at a certain theta. Now, so what's the equation for x? It's going to be x equals a sine theta. Now we know that the change in angle, that angle that is in that triangle, okay, we can actually find it for any time, and we find it from omega t, okay, where omega equals change in theta over time. So omega t, since it's rotating, therefore the displacement object undergoing SHM is given by x equals a sine omega t. Okay. Now you think about it, this thing will be a maximum when you are at what sort of angle? Okay, so once you're at the top there, then you're going to have the maximum sine. In other words, this whole thing gets to 1 at a certain position, and that is when it's at 90 degrees. Well, not really talking about 90 degrees, but pi over 2. The displacement varies sinusoidally referred to the reference circle. Okay. Now if we differentiate our equation that we just had, okay, so differentiating sine goes to cos, okay, and differentiating cos goes to minus sine. So if we differentiate our displacement, we actually find velocity. So velocity is equal to a omega cos omega t. Okay. Now if we differentiate velocity, acceleration. Okay, so what's the differentiation of acceleration? It's going to be a equals negative a omega squared sine omega t. So hopefully you see that. Now, what we're going to do is look at a relationship between the acceleration one and the displacement one. So the acceleration equation and displacement are these: x equals a sine omega t, and a equals negative omega squared a omega squared sine omega t. Now if you compare those two, we've got two similar wordings. They've got sine omega t on each one, okay, so similar terms, and you can then compare the two. So if you do compare the two, make them equals, then you actually get left with a equals negative omega squared x. Okay, and this is actually the defining formula, which we'll come to later.